Hello and welcome to this lecture. We've been looking at diagonalizability and when a diagonal matrix can represent an operator and all of that. And it's also very related to this general topic of diagonalizing matrices. So let's look at some examples of matrices and diagonalization and determining when a matrix is diagonalizable and all that. Let's get started. Okay. So diagonalizability is what we will check. We've already seen the theory based on the conditions on the eigenvalues and eigenvectors when a linear transformation has a diagonal matrix representation. So that condition, we'll look at some examples and see how in what form it can be used. Okay. So here is the first example. We'll pick lower triangular examples to start with because triangular matrix are nice. This is very nice. You can do computations easily, but and most of the, in fact, all of the non-trivial examples will come in the triangular matrix itself. So we'll begin with that. Here's a very simple matrix that of course represents a linear transformation. As we know, you've got 1, 2, 3 on the main diagonal. For this simple matrix, finding eigenvalues is quite straightforward. You have to look at determinant A minus lambda I, and that will end up being 1 minus lambda, 2 minus lambda, 3 minus lambda. It's quite easy to see. So the eigenvalues we see are 1, 2, 3. So you have 3 distinct eigenvalues. So from your conditions, you know immediately that this is a diagonalizable matrix. We call it a diagonalizable matrix. Of course, it represents a diagonalizable linear transformation. Okay. So, what exactly would be the diagonal matrix representation? We'll see that later. At this point, we're just going to look at diagonalizability and various different forms it can take in actual examples. Okay. So, what about eigenvectors? You can go ahead and find the eigenvector. The eigenvector for 1 corresponding to 1, you have to do A minus lambda I and find the null space element there, and that is easy to do, right? So when you subtract 1 from here, you're going to get 0, 1, 2 here, and then so you see 0, 1, 1, 0, 1, 1. So this is going to be 1 minus 1, 0. So likewise, you can subtract 2 and then find the null space basis, subtract 3 and find the null space basis. You will get the 3 eigenvectors. I'm not showing you the details here, but this is easy enough to do. And clearly enough, you see, we already knew this would happen, right? If you have distinct eigenvalues, clearly you will get eigenvectors which are linearly independent, and there are 3 of them here, right? So this is R3, right? This is this matrix represents the transformation from R3 to R3. So this has got 3 linearly independent eigenvectors, so which means you have an eigenvector basis. Okay, so of course that's what diagonalizability means, isn't it? So in the distinct eigenvalue case, these things work out in a very simple fashion. Okay, so let's look at a slightly different example where this 2 in the middle, right, in this expression there was this 2 in this matrix, there was 2 in the middle entry. So I'm going to make it 1. Okay, if you make it 1, again the determinant A minus lambda I and eigenvalue calculation is very simple, but now you have repeated eigenvalues. You've got 1, 1, 3. Okay, so from here you just know eigenvalues are not distinct. So from here you can't directly conclude diagonalizability, right? You have to go ahead and check how many eigenvectors you will have. Okay, so now you have to find eigenvectors, and if you do that, you see, if you do look at eigenvectors with eigenvalue 1, you find only 1. Okay, you don't get 2 linearly independent guys, right? So you get only 1 of them. So the nullity of determinant A minus I will end up being only 1. Okay, so you can see that if you subtract 1 from the diagonal, you're going to get 0, 0, 2, and that's got rank 2, no? 1, 1, 1 is there. So this has got rank 2, which means nullity is 1. So the eigenvalue 1 has only 1 eigenvector, doesn't have the second linearly independent one. Okay, 3 of course is different from 1, so it will have 1 eigenvector, and that's okay. Okay, so we see here now there are only 2 independent eigenvectors, which means there cannot be an eigenvector basis for this matrix or this the linear transformation that is represented by this matrix. Okay, so you conclude that this is not diagonalizable. So this matrix, the linear transformation that is represented by this matrix does not have a diagonal matrix representation for any basis that you choose. Okay, so this is a very simple example that you can come up with. Okay, so let's look at a slightly different example from the previous one. So this left entry here, this guy was 1, right? So I'm going to make that 0. So I make that 0, then the diagonal values have not changed. This is triangular, so eigenvalues remain same. Again, I cannot conclude at this point whether the matrix is diagonalizable or the linear transformation is diagonalizable. Okay, so I have to compute the eigenvectors. So now if you compute the eigenvectors for 1, when you subtract 1, you notice you got 0, 0, 2 here. So the rank of A minus I now becomes only 1, which means nullity is 2, and you can find 2 linearly independent eigenvectors here. Okay, so you can go ahead and do that, the standard method, this was described earlier. So you just plug it in, substitute, you'll get 2 linearly independent eigenvectors for 1. Okay, so likewise 3 remains the same, you get the eigenvector corresponding to 3. So now for the same set of eigenvalues, because of the small difference here that I made, I have 3 independent eigenvectors, which means my matrix now is diagonalizable, and I can proceed. Okay, so I hope you see how the different cases come. When the eigenvalues are distinct, immediately diagonalizable, no problem. If you go ahead and find the eigenvectors, they'll end up being linearly independent. If they are not distinct, then you have to do the additional work of finding the nullities, finding the A minus lambda I, the nullity of that, the null space vectors of that, and only then you can conclude whether it's diagonalizable or not. You don't need to find the vectors themselves, you just need to find the nullity of this A minus lambda I. If you do that, from there you can find out diagonalizability, right? So it's a question of finding the geometric multiplicity for these eigenvalues. Okay, so those are lower triangular examples. Let's see a slightly more general example just for fun. Okay, so here is a symmetric sort of example, 1, 1, 1 here. We saw many of these matrices we saw earlier when we were computing powers. So I'm sort of using the same matrix here to make sure that we cover all the examples in detail. Okay, so if you look at this guy, you have to now find determinant A minus lambda. If you do that, you will get this kind of an expression. From here you can conclude eigenvalues are 0, 1, 2. Okay. You might have concluded from here various ways to find eigenvectors and eigenvalues. So it's probably you can see 0 has to be an eigenvalue because rank is 2, right? So these two columns are the same. So, and then 1 has to be an eigenvalue because the second column is 0, 1, 0, right? So that means 1 is an eigenvalue, and then 2 will become an eigenvalue, and so on. Okay, so this is something that's important. Okay, so we've got eigenvalues 0, 1, and 2. Okay, so these are distinct eigenvalues, so it immediately becomes diagonalizable. Okay, so you don't have to do any more work to determine diagonalizability because I've got distinct eigenvalues. So sure enough, if you go ahead and find the eigenvectors corresponding to these eigenvalues, they end up being linearly independent and they end up becoming a basis. Okay, so you can repeat these examples. I'm just providing more examples just to show you the flavor of how these may happen. Here is another example where you get repeated eigenvalues. Okay, so this is again not triangular, but you get repeated eigenvalues 1, 1, 4. So you can't conclude diagonalizability, you have to actually find the nullities and all that. And if you find for eigenvalue 1, you actually have 2 linearly independent eigenvectors. For 4, you have only 1. Of course, you have only 1. So you have 3 independent eigenvectors. So you have a basis. So from here, you conclude it's diagonalizable. Okay, so I mean, you don't need to, like I said, you don't need to find these vectors explicitly. You just need to find the geometric multiplicity of 1, and for that you need the nullity of A minus I, right? So that's what you have to find here. Okay, so here's another example. I'm just going to go through this very quickly. So you see 1, 2, 2 are the eigenvalues are not distinct, and only 2 of them result. The geometric multiplicity for 2 is only 1, so you get only 1. So you can check all these things by the calculation. So this is not diagonalizable. Okay. So let's conclude with one of these examples we saw for the power calculation, where you have A on the diagonal and then B on the lower diagonal. And see here, if you look at determinant A minus lambda I, you get A minus lambda power 3, which means the eigenvalue A is repeated 3 times. So it's not distinct, so it's not clear at all that it's diagonalizable. You have to find the eigenvectors. So now eigenvectors depends on the value of B and C. If B is not 0, okay, so if B is not 0, when you do A minus small a capital I, so diagonal values will go off to 0, so you'll get 0, 0, 0. If B is non-zero, you have 2 non-zero values here, which means the rank of that is 2, nullity is only 1, so you'll get only one independent eigenvector, so this will not be diagonalizable. If B is 0 and C is not 0, you will get only 2 eigenvectors, because again the rank of A minus small a I will become 1 and nullity will become 2, you will get 2 of them. Again, it's not diagonalizable. The only way this is diagonalizable is B and C are 0. So of course, clearly the matrix itself is diagonal, and you can also find that there are 3 independent eigenvectors. Okay, so those were the examples. So let's just quickly go with the last 2 examples we saw, these unusual examples of lower triangular, where you had this repeating pattern for A power k, right? So for this guy, if you see, the eigenvalues are distinct. Okay, and then clearly this is diagonalizable. You can find the eigenvectors and confirm that it's so. Here is the last example. This is actually very similar to the A example, where A is 0. Now A is 0, and small a is 0, right? So diagonal values are 0, b is 1 and small c is 1, right? So that's what it is, and you see that eigenvalues are 0, not distinct, but there's only one eigenvector, so this is not diagonalizable. Okay, so I was just trying to show you various different examples of what can happen, and hopefully this is clearing up some of those actual ways to use the definition of diagonalizability for you. Okay, thank you very much.